Air movement. This class will explain physics we need to know for a vacuum system to work efficiently. Sewer combination trucks or industrial vacuum trucks all rely on the same basic physics. In our industry, we say or call our trucks vacuum, but they are air-moving trucks. They are conveyor belts, but use air, not rubber belts, to move material. This class is not limited to industrial trucks. Any type of equipment that moves air for the purpose of material removal, these same physics apply. It could be a regenerative air or vacuum street sweeper, hydro-excavator truck or trailer, sweeper scrubbers, or leaf loader, a shop vac, or a vacuum cleaner you use in your house. Some systems do use pure vacuum to work. These are pumper trucks that evacuate the air from a debris tank and use vacuum to pull material up a hose. This class will explain the limitations to this system. Pressure. Our weather system is affected by highs and lows of air pressure. High pressure brings clear, warm weather. Its symbol is a capital H on a weather map. When the pressure is above average is what high pressure is. High pressure systems move faster than low pressure systems. Low pressure brings clouds and cold weather. Its symbol is a capital L on the weather map. When pressure is below average is what low pressure is. Low pressure systems move slower than high pressure systems. High pressure is trying to equalize itself out with low pressure. Very high and very low pressures can create wind turbulence called hurricanes. If we take a balloon and tie the end, place it in a vacuum chamber, then remove the air around the balloon, what will happen? Will the balloon get smaller or will the balloon get bigger? The pressure inside the balloon is higher than the air in the vacuum chamber. The higher pressure will try to go to the lower pressure. The balloon will get bigger. Pressure is measured in different ways. Pascal, torr, bars, inches of mercury, atmosphere, inches of water, pounds per square inch. In our application, we use the following measurements. Pounds per square inch tells us what the pressure is in a pipe or a hose, how much pressure you put in your tires. Inches of mercury is what we use to measure vacuum. It is a measure of how high a column of mercury raises in vacuum. Your sewer trucks might be designed to lift 18 inches of mercury. Or you'll hear the term used, your truck is an 18-inch blower. The most vacuum possible on Earth is 29.9 inches of mercury. There are blowers that are available that will do 27 to 28 inches of mercury. The mercury barometer is the oldest type of barometer to help predict the weather. Pressure is defined as a force per unit area, and the most accurate way to measure low air pressure is to balance a column of liquid of known weight against it and measure the height of the liquid column. The units of measure commonly used are inches of mercury, using mercury as the fluid, and inches of water, using water or oil as the fluid. In its simplest form, the manometer is a U-tube about half filled with liquid, with both ends of the tube open. The liquid is at the same height on each leg. When positive pressure is applied to one leg, the liquid is forced down in that leg and up in the other. The difference in height, which is the sum of the reading above and below zero, indicates the pressure. When a vacuum is applied to one leg, the liquid raises in that leg and falls in the other. The difference in the height, which is the sum of the readings above and below zero, indicates the amount of vacuum. Inches of water column gauge is used to measure low strength of vacuum and pressure. It is a measurement of how high a column of water raises in a tube. Water being about 14 times lighter than mercury. This is a barometer that changes water level due to change in weather and atmospheric pressure. A Magnehili gauge is used in AC and filtration. 1 inch of mercury is equal to 13.59 inches of water column. What is the highest a pump can raise water? A pump suction is not a force, but simply a removal of an opposite force to the force of air pressure on the surface of water. When you stick a pipe into a pool of water, air inside the pipe is pushing down on the water in the pipe, and air outside the pipe is pushing down on the water outside of the pipe, so water level is in balance. But now let's suck out the air inside the pipe. The water is pushed up the pipe by the air pressure that is outside the pipe, but there is no counteracting force pushing the water down, so it is being raised inside the pipe. But why does water stop raising? The water is pulled down by gravity. The more water in the pipe, the more it weighs. Since the force of the air outside the pipe is not changing, eventually the weight of the water is equal to the air pressure outside the pipe, and everything is in balance again. Water is pumped from a well by creating a partial vacuum above the water by the pump. The amount of vacuum in inches of mercury is equal to the weight of the column of water from the water table in the well to the surface. Atmospheric pressure at sea level is 29.92 inches of mercury. This is equivalent to a column of water 406.7 inches or 33.9 feet. Therefore, a total vacuum can only pump water from a depth of just 34 feet. And that is why a pump or a vacuum truck is limited to how deep it can pump fluids. Mercury versus water column. If we were to use an 18-inch blower to raise a column of water, how high would the water lift? Take the water column of 13.59 and multiply it by 18 inches, which equals 244.62 inches or 20.38 feet. This number can be rounded off to the nearest foot. If you figure that every inch of mercury is equal to 1 foot of water column lift, so your 18-inch blower can be roughly figured to lift 18 feet. The vacuum I'm using is a VacMaster. Its specs are: max airflow with supplied hose is 58.5 cubic foot a minute. Sealed water lift is 62 inches. I should be able to pull around 60 inches or 5 feet. Putting a 1-inch hose in a container of water. The vacuum should raise this water 60 inches. Look at the gauges and the tape measure. We will demonstrate water lift in this hose and compare the gauge to the tape measure. The water raises to a capacity of the vacuum. The white mark is at 60 inches. The Magnehili gauge is at 60 inches of water column. And the mercury gauge is at 5 inches of mercury. Friction loss. Friction loss in a hose is due to friction of a material going through the hose. This can vary depending on the type of material that is going through the hose and the type of material the hose is made of. The inside surface contour. Example, smooth versus corrugated. Friction loss is also from the length of hose. The longer the hose, the more friction loss there will be. And there is an increase of friction loss with the increase of flow of material going through a hose. A smaller diameter hose will have higher friction than a larger diameter hose. To demonstrate friction loss in hose size, we have 3 sizes of hose all in a container of water: 1 inch, 3/8 inch, and 1/4 inch. Under same vacuum. Which one pulls fastest? Shut off vacuum, they will equalize. The 1-inch hose is the winner. Even though it has more water to lift, there is less friction. When the vacuum reaches a maximum, the water levels in each hose equalizes. Viscosity. Viscosity is the density of a liquid. The thicker the material, the slower it will move up the hose. If we were picking up heavy, thick sludge or grease, adding water to thin it out would save us time on picking it up. However, that could cause more trips to the dump. In this demo, using oil and water in 2 hoses of the same size and length connected to the same vacuum source. The 2 hoses are 1/4 inch ID. Which one will travel up the hose faster? Turn the vacuum on and we see the water went up and stopped before the oil did. Fans versus blowers. Fans move air in higher volume and speed. Fans move dirt faster away from worksite. Fans need less water to move regular dirt faster. A fan will move around 20,000 cubic foot a minute of air. Blowers pull slurry-type materials over long distance. Blowers can be submerged to vacuum material. Blowers need higher water usage for effective vacuuming. A blower will move around 3,200 cubic foot a minute of air. Filtration. Filtration is done in 2 different ways. Our sewer trucks are designed for wet materials only. Industrial trucks have a baghouse to keep light particles of dust from entering the fan or blower that can cause expensive damage. Debris body. The first stage of filtration is the debris body. As air is pulled out of the body, the debris and air coming in is through the debris boom hose. When the speed of the air enters the large body, the airspeed slows down and the debris falls out of the airflow. The cleaner air is then screened and exits the body. In sewer or hydro excavation, the material must be wet enough to gain weight for it to fall out of the airflow. How all of this applies in different types of bodies. Debris enters the top of a body from a boom hose, slows down, and drops out of the airflow. Then goes through the screens and onto the fan or the blower and exhausted. Another design is where the debris enters the front of the body. As the airspeed slows down, the debris is helped downward with the use of deflectors. The cleaner air goes to the screens and out to the cyclones, then to the fan or blower. To demonstrate using rice, you can see that the rice falls out when entering the body. When the air speed increases, the deflectors sends the rice downward. Very little is going out the outlet. If equipped, cyclones are the second stage of filtration. The air that is pulled from the body goes through the cyclones. It makes contact with the inner cone, and friction slows and causes the debris to drop down to the cleanout. The cleaner air goes up and out the center at the top of the cyclone. To demonstrate using flour, you can see the contact to the walls causing the flour to drop. This is just for demonstration. There should never be this much material going through a cyclone. The third stage of filtration is a microstrainer found on blower units only. The strainer is protecting the blower if anything large that gets past the prior stages. The air movement is created by the blower. The air is pulled through the microstrainer, then into the blower. The blower exhausts out the opposite side to the silencer and exhausts to the atmosphere. Fans will not have a microstrainer or a silencer. Reducing hose size. What happens when hose is reduced to a smaller hose from a larger hose? Hose diameter. Question. Is a 4-inch hose half as big as an 8-inch hose? The diameter is half, but the area is 1/4. The formula for the area is area equals pi r squared. Pi equals 3.14. Area of an 8-inch hose, 3.14 times 4 times 4 equals 50.26 inches. Area of a 4-inch hose, 3.14 times 2 times 2 equals 12.56 inches. 50.26 inches divided by 12.56 inches equals 4. A 4-inch hose is 4 times smaller than an 8-inch hose. The area of a 6-inch hose, 3.14 times 3 times 3 equals 28.27 inches. A 6-inch hose is 1.77 times smaller than an 8-inch hose. Area of a 2-inch hose, 3.14 times 1 times 1 equals 3.24. A 2-inch hose is 15.5 times smaller than an 8-inch hose. The point is, use the largest diameter hose that you can. Hose size change dropout. When the air speed of a smaller hose slows down into a larger hose, the debris drops out and plugs up the larger hose. Just like how the debris body works. The air velocity needs to increase to carry the debris to the body. An air gap needs to be in place where the hose is reduced. Going from an 8-inch hose to one 4-inch, use an air gap. Or going from 8-inch to 4 4-inch hoses to equal 8-inch. Or use the same size hose all the way to the truck. As we use the smaller hose, you can see the debris body is still empty. What is happening is like the debris body, the airspeed slowed down, the material dropped out. When we removed the small hose, the increase of airflow pulled all the material that had stayed in the hose. Here we reduce to 2 hoses. There is no drop out and the job is done faster. Air conveyance for underwater. For either system to pull further, we need to induce air to convey the material greater distances. The Higby nozzle is typically used with a fan machine. There is a 3-foot and a 6-foot length available. Between the inner tube and the outer tube is an air gap that allows the air to go to some holes close to the end of the inner tube. This air carries the debris to the debris body. An air gap is typically used with a PD blower. Longer vacuum tube can be used for deeper pulls. The band around the middle of the air gap allows you to adjust the amount of air that is needed to pull from different depths. If your blower is set for 15 inches, you could vacuum 15 feet underwater. With the air gap as close to the top of the water and a known depth of the water, the band on the air gap will be adjusted for the inches of mercury to how high we need to lift the water. 1 inch of mercury equals 1 foot of water column. Thank you.